So the previous section talked about how to write the formulas. This one is how do we name the compound given the formula. So there are different naming systems for different types of compounds. And this is somewhat similar, or it's analogous to how there are different patterns that people use for naming their children in different countries. My ancestors came from Sweden. I don't believe they do this anymore, but when anyway, in the past what they did is if your father's name was Peter and you were a boy, your last name would be Peterson because you're the son of Peter. So if your name is Lars Peterson and you have a son, his last name is Larson. And so the last names changed every generation. For girls, they took also the father's first name, but then instead of son, it was daughter, D-O-T-T-E-R. So if your dad's first name was John, then you would be, Cindy, John's daughter. And it kept going like that. So it makes researching a genealogy a bit challenging. But that was their pattern. In the United States, that's not the pattern that we use. Whatever the father's last name is, that's the name that's typically given to the children. So it's just a different country, a different pattern of naming. You get into the Asian countries and they use different rules. And we all are like, oh, okay, that's how they do it. So for naming compounds, we have a different system of naming for different types of compounds. And the reason we need different systems is because it actually makes it easier. If we tried to apply the same system to all the different types of compounds, it would get really ugly. So we just have to go with it. We've got to identify the compound. Now, there are two compounds that use a common name always, and that's water and ammonia. So water is H2O. I think if you didn't know that before, we've used that as an example enough that you should know that. So water is H2O, and ammonia, which I know you've heard of, is NH3. And you just memorize that. Everything else has a systematic name, and it may or may not have a common name, kind of like a nickname. But we're going to learn how to do the systematic names. So, first of all, we're going to talk about naming the ionic compounds. You have to identify it as an ionic compound. So if you have a metal and one or more nonmetals, it's an ionic compound. The exception that we need to remember is that if it has NH4 plus in it, it's also an ionic compound. This is the ammonium ion, and it's nitrogen and hydrogen. These are nonmetals, but it's an ion. Okay? Sorry, I don't like exceptions either. I'm not a fan of this division, but it's in the book, so we're going to go for it. So ionic compounds, metal and nonmetal, and those can be broken down into two different categories. One's where the metal only forms one kind of ion, and one where the metal forms more than one kind of ion. This is the ones we've been looking at so far with the main group metal ions. We can predict their charge from the periodic table. So, ions with predictable charges. We've got the group 1A metals, the group 2A metals plus 2, the group 3A metals plus 3. This is the periodic table I was wanting earlier. Zinc and silver. So groups 1A, 2A, 3A, zinc and silver. Well, so how do you remember zinc and silver? Here's zinc, and here's silver. So it's going down the stairs. 3, 2, 1. So zinc is 2 plus. There's not a lot of space in there. And silver is plus 1. So I'm going to chant this many times today. Groups 1A, 2A, 3A, zinc, and silver. They form one type of ion. The name of those ions is just the element name. So the name of this ion is zinc ion. This is silver ion. This is magnesium ion. Okay, everybody okay with that? Oh, look, there's the triangle. I forgot I had animations in here. So here's a table from your book showing those. Personally, I don't think this table's that useful. I much prefer just remembering the parts of the periodic table, groups 1A, 2A, 3A, zinc, or silver. Anything else, any other metal can form more than one ion. And so in the name of that ion, we have to somehow specify which ion it is. And what we do is we use Roman numerals. So this is not unlike, the King Henry of England, right? There's a whole bunch of King Henrys. How do you distinguish between the King Henrys? Well, there was King Henry I and King Henry II and King Henry VIII, right? And they had Roman numerals after their names. So that's what we do with these other ions. So iron makes a +2 ion and a +3 ion. And you might say, why? And my best answer right now is, because it does. Explanation is way too long. So iron 2+, that's called the iron 2 ion. Whatever the charge is, the Roman numeral is the same. So iron 2, and when we read this, we call this iron 2 ion. So Fe3+, that's iron 3 ion. Okay? So let's maybe throw in an example here. What would Cr3+ be named? Chromium 3 ion. So chromium, and then Roman numeral 3 in parentheses, ion. So here's a table from your book showing some of the metals that form more than one ion and their common charges. You do not need to know that chromium forms a +2 and a +3 ion, that it doesn't do +1 or +4 or +7 or anything like that. You don't need to know what they form. That will be shown either in the name or from the formula. We figured that out. This is an older system of naming that we might run across, but you do not need to learn it. So chromous and chromic. The us is the lower charge and the ic is the higher charge. It's there, it's historical, but we don't need to learn it. Roman numerals. They used to be on clocks all the time, but now not so much. So this IV, right? That's the Roman numeral 4. Roman numerals are kind of weird. So 1 capital I is the number 1. And for 2, it's 2 capital, oops, that's not 2. 2 capital I's. And the number 3 is 3 capital I's. And you think, okay, this is just like tally marks, right? We just keep going and going. Well, let's skip ahead and look at 5. 5 is a V. If you want to know why, go research ancient Rome. I don't know why they did it like this. And then 4 is 1 less than 5. So it's 1 before 5. And 6 is 1 after 5. So VI. And 7 is VII. And we're not going to run into anything past that. There's your brief lesson on Roman numerals. So any questions about those guys? Okay. You do not need to memorize these guys. You need to understand how they're named, that the Roman numeral tells me what the charge is. You just need to understand that. We don't use Roman numerals for groups 1A, 2A, 3A, zinc, or silver because it's not necessary. It's extra writing that's not needed. Okay? If you pick an answer that has a Roman numeral on a test when there shouldn't be a Roman numeral, that would be considered incorrect. Okay? So the anions. We talked about the polyatomic anions, nitrate, nitrate, those guys. The monatomic anions, we've learned how to do their charges. Now we need to learn their names. So fluorine, we know from its position in the periodic table, is going to have a -1 charge. When we make this into an ion, we change the ending of the name. So fluorine becomes fluoride. Bromine becomes bromide. Oxygen becomes oxide. So it's usually just taking off the ending of the name. Oftentimes it's the last syllable, but sometimes it's 2 syllables. And you could try saying oxygide, but wait a minute, that doesn't sound right. It's oxide. Sulfur becomes sulfide, and nitrogen is nitride. Again, nitrogide sounds really weird. So this is where the masculine metals and feminine nonmetals kind of works out nicely. So traditionally, a man and a woman get married, and what does the woman do to her last name? She changes it. So here, when these nonmetals become part of a compound, it's a little bit like they're getting married to the metal, and so they change the ending of their name. The metals don't change the ending of their name. Okay? Questions? So, in this class, all of the ionic compounds we're going to look at have 2 ions. 1 cation, 1 anion. Just 2. There are ionic compounds that have more than 2 ions. We don't have to learn anything about them. So when we name the ionic compound, we just take the name of the cation followed by the name of the anion. So usually the cation is just the first element because it's a metal. It's going to be monatomic, and there's just one. The only exception is when the first ion is NH4. And you could do really well in this class without remembering that. So the first element's the cation, the anion is everything else. Students sometimes try to make 3 or 4 ions out of this. Two ions. 1 guy, 1 girl. This is not Utah many, many years ago, okay? There's no polygamy here. 1 man, 1 woman, and whatever. Okay, so naming these compounds. So KBr. So the first element is K. That's a metal. That tells me this is an ionic compound. And so there's 2 elements here, so this is fairly easy. We've got 2 ions. We've got K and we've got Br. So what would the charge on this is potassium. What would the charge on potassium ion be? +1. And on bromine, -1. We didn't have to do that, but extra practice. So what's the name of this ion? Potassium. So the first part here is potassium. It doesn't need a Roman numeral because it's in group 1. Group 1A, 2A, 3A, zinc and silver, no Roman numeral. This is the element, bromine. When it gets married to potassium, it changes the ending of its name and becomes what? Bromide. So that's potassium bromide. Questions? It's always lowercase. So this is the name of a compound. It's not a proper noun. The only time the first one would be capitalized is if it's at the beginning of the sentence. Okay, so not capitalized. There's a space in between. Most ionic compounds, just like most people, have 2 names, a first name and a last name. And here the first name is the name of the cation, the second name is the name of the anion. So let's look at this one. So again, this is a diatomic compound, 2 atoms only, 2 elements. So We've got Zn, and we've got N. Let's put the charges on them, not that we need to, but just for practice. What's the charge on a zinc ion? +2. Okay, 3 plus is tempting because there's this 3 down here. But that 3 tells us how many there are, not the charge. How do we know the charge? Position on the periodic table. Aluminum, zinc, silver going down the stairs. 3, 2, 1. Okay, so that's why it's +2. And what's the charge on nitrogen? -3. So that's just practice. Okay, so what's the name of this ion? Zinc. Does it need a Roman numeral? No, it's in group 1A, 2A, 3A, zinc or silver, right? Those don't need Roman numerals because there's no confusion. They always have the same charge. So this is nitrogen. What does the name change to? Nitride. So this is zinc nitride. Questions? So if you have one of those other metals, not in groups 1A, 2A, 3A, zinc, or silver, you have to figure out what the charge is from the chemical formula. So you're going to look at the charge on the anion, and then the sum of all the charges has to be 0, and so you kind of have to figure it out. There are multiple ways to figure this out. I'll show you a couple. You need to find the one that makes sense to you, okay? And if none of my methods make sense to you, ask me in lab today, and I will find one that makes sense to you. So, looking at this compound, Fe2O3. So, is iron in groups 1A, 2A, 3A, zinc, or silver? No. That means it can have more than one charge, and we can't predict the charge from the periodic table. The formula is giving us clues about the charge. So we've got iron and we've got oxygen. We can predict the charge on the oxygen. What is it? -2. And we've got 3 oxygens. So I'm just going to draw them out because I like pictures. I like visuals. So from those 3 oxygens, what's the total negative charge? -6, right? 3 times -2. And then for the iron, this subscript is not the charge. It's how many there are. So there's 2 irons. We don't know what the charge is, but we do know what the total charge of those 2 must be, right? If we've got 3 of these with a total -6 charge, those must add up to +6 because the compound's neutral. Does that make sense? So we've got +6, and we need to divide this evenly between those 2. 6 divided by 2 is what? 3. So we figure out that each of these is 3+. The first few times it's going to take a while. Once you get the hang of it, it's not that bad. So if we were going to name this compound, what's the name of this ion? Iron 3. It needs a Roman numeral because it is not in groups 1A, 2A, 3A, zinc, or silver. I told you I was going to say that a lot. And what's the name of this ion? Oxide, right? So that's iron 3 oxide. Questions? So let's do some practice. PbO. So let's just start naming it. Pb is the symbol for what element? Lead. So it's going to be lead. Is lead in groups 1A, 2A, 3A, zinc, or silver? Nope. That means it needs a Roman numeral. So I don't know what that is right now, but I don't want to forget to come back to that. So I'm going to put the parentheses in there and leave some space for the Roman numeral. What's the name of this ion? The element is oxygen, oxide. Okay, so I have lead something oxide. I need to figure out what the charge is. I do that by looking at the two ions. What's the charge on oxide? -2, 2 minus. So the total, there's only one of them. The total here is -2, so the total positive charge has to be what? +2. And there's only one ion, so it's got all of that. This must be 2+. You see how that worked? So what Roman numeral do I put in here? 2, because it's the charge on that ion. Questions? Let's look at this one. So Cu is the symbol for what? Copper. Is copper in groups 1A, 2A, 3A, zinc, or silver? Nope. So we need a Roman numeral. Don't know what it is. It's okay. We'll come back to that. S, sulfur. What's the name of the ion? Sulfide. So this is copper something sulfide. And we need to look at the charges here. So I've got Cu, and I've got sulfur, and the charge on sulfur is 2 minus. The chemical formula tells me I have 1 sulfur and 2 coppers. Okay. Total negative charge is -2. What's the total positive charge? +2. Taking that and dividing this +2 charge between these 2 copper ions, what is the charge on each of them? 1. The math here is very simple. It's remembering what to do with it and trying to see what the pattern is. So then the Roman numeral is 1. So this is copper 1 sulfide. Questions? Yes?
Why is it that on the other one we didn't do that? We just did it 2.
On this one?
Yeah.
Okay, so from the formula, I can see that there's only 1 PB. So there's 1 PB here, but Cu2, there's 2 copper ions. Okay? Good question. And so then the total positive charge gets divided among both of them. And it has to get split up evenly, because if you've got more than 1 ion, they're going to be the same charge. You're not going to have one that's copper 0 and one that's copper 2+. They're going to be the same. Yes?
So we have Cu subscript 2 and subscript 1.
Yes.
Can we just split the 1 with the 2?
You can. So that's uncrisscrossing. It's reverse crisscross. That works a fair amount of the time. It doesn't work all the time. So if that makes sense to you, you can use that. But just be careful, because it can backfire. Any other questions? Okay, so let's look at those polyatomic ions and learn some shortcuts so that you don't have to memorize the whole table. Most of those polyatomic ions are called oxyanions. They are anions that contain oxygen. And there are patterns in those oxyanions. So we can have a series like there's nitrate and nitrite. And looking at these formulas, what's the only difference? The number of oxygens. The number of nitrogens is the same. There's 1 in each. The charge is the same. Both of them are -1. This one has 3 oxygens. That one has 2 oxygens. Same pattern with sulfur, although the charge and the numbers of oxygens are different. This is SO4 and it has a 2- charge, but this is SO3, also has a 2- charge. The only thing that differs between them is the number of oxygen atoms. The charge stays the same, the number of the other elements stays the same. So the approach to learning these is you memorize the one that ends in 8. So nitrate, you just flat out memorize that. You put that on your index cards. You put nitrate on one side, you put NO3 minus on the other. Then you learn the pattern and you can figure out the other ones from the nitrate. Nitrite has 1 fewer oxygens. Turns out to be 1/3 fewer oxygens. Bud Light has 1/3 fewer calories than regular Budweiser, right? That's what the commercials say anyway. I don't drink the stuff, but Bud Light has fewer calories. Nitrite is the light version of nitrate. It's got fewer oxygens. Sulfite is the light version of sulfate. 1 fewer oxygens. So this is phosphate. You just have to memorize it. What would the formula for phosphite be? PO3, 3 minus. Just 1 fewer oxygens. So you memorize one, and then the other one is related to it. You don't have to memorize the other one. Any questions about that? Yeah.
How do we know that it's not NO4?
How do we know that nitrate is not NO4 minus? Because we memorized that nitrate is NO3 minus.
Yeah, so that's like a high.
Well, it turns out there isn't an NO4, but you don't need to know that. So I'm going to show you here that some of them do have an O4 and an O with just 1. You could apply the same pattern of naming to all of them. You don't need to know which ones exist and which ones don't. I will only give you questions about ones that actually exist. So there's just no opportunity to screw up on that one. So here are chlorine, bromine, and iodine. They have series that are larger. So nitrate and nitrite are the only 2 in the nitrogen series. Sulfate and sulfite, the only 2. Well, actually, no, I lied. Never mind. But again, you don't need to know that. So here's chlorate. So chlorate is ClO3 minus. Why? Because you memorize it. Chlorite is the light version. It's got 1 less oxygen. And then we've got hypochlorite. Hypo is a prefix that means below. Hypodermic needle. Hypodermic literally means below the skin, right? It goes under your skin. So hypochlorite has 1 less than chlorite. Perchlorate has 1 more than chlorate. So I remember that as hyper. A hyperactive child is extra active. It is more active, right? So per is just a shortened version of hyper. It means more. So perchlorate has 1 more oxygen. So there's a pattern here. Chlorine, bromine, and iodine are all members of which family on the periodic table? The halogens, group 7A. They're nonmetals, so I think of them as feminine. I think of them as sisters, right? So these sisters, chlorine, bromine, and iodine, make similar compounds or similar polyatomic ions with oxygen. Chlorate is ClO3 minus. Bromate is BrO3 minus. Iodate is IO3 minus. So really, if you memorize chlorate is ClO3 minus, you get this pattern in your head, and you say, oh, well, bromine is chlorine's sister. She does the same thing. Iodine is chlorine's sister. She does the same thing. There you've got 12 ions from 1, just making patterns. Okay? In mastering chemistry, when it asks you to name these, it does want the word ion after it. Personally, I don't care if you put the word ion on a worksheet or on an exam or something. Chlorite or chlorite ion, I'm fine with that. Mastering chemistry is picky about that, so it wants the ion. Okay, any questions? These polyatomic ions show up in lots of everyday products. Clorox bleach is sodium hypochlorite. We could write the formula for that. Let's do it. What's the formula for sodium ion? Na plus. Hypochlorite. So chlorite is ClO3 minus. That means chlorite is ClO2 minus. And hypochlorite is ClO minus. How do we put those two together? Just push them together. The charges are equal but opposite, +1 and -1. So NaClO. That's sodium hypochlorite. That's the bleach part of bleach. Most of it's water, but it's about 5% of this stuff. Sodium bicarbonate is baking soda. Calcium carbonate is used as an antacid. Sodium nitrite is a preservative for packaged meats. Is nitrite good for you? No, but botulism's worse. Mm-hmm.
That negative, that's the ions, right?
These are the ions. So sodium has a +1 charge, and hypochlorite has a -1 charge.
Oh, I was just looking at the oxygen.
Yeah, so they're together. It's polyatomic. When we look at a formula like this, there's 3 elements there, right? And this is where sometimes students want to make a sodium ion and a chloride ion and an oxygen ion. That would be 3 ions. You can't do this in that. Do that in this class. 2 ions only. So the sodium is the first one, and everything else is the second one. This is a polyatomic ion. So seeing this bicarbonate reminds me we didn't really talk about those guys. Let's look at the table, which is way the heck back here. Okay. Going back to this table, you'll notice that most of these end in ate or ite, and most of them are just one word, but then there's like this one, hydrogen carbonate or bicarbonate. So bicarbonate is an older term which is still widely used. We need to be familiar with it. I'm going to use hydrogen carbonate because I think it's more straightforward and more descriptive. So here's carbonate, and here's hydrogen carbonate. They're kind of similar, aren't they? They both have 1 carbon, and they both have 3 oxygens. The charge is different, though. So let's talk about hydrogen. Hydrogen's a squirrely little brother, right? So if hydrogen makes a cation, what do you think its charge would be? Where is it on the periodic table? It's in group 1A. So it does form a +1 ion. A hydrogen ion is an H+ ion. So if I put an H+ ion with a carbonate ion, where can I write this? Let's do it over here. So H+ and CO3, 2-. I'm not trying to make a compound. I'm just going to shove them together. If I shove them together, I get HCO3, and I've got a +1 charge and a -2 charge. When I add those together, what do I get? -1. The hydrogen carbonate ion is the carbonate ion with a hydrogen ion put together. So hydrogen carbonate. That's why I like hydrogen carbonate better than bicarbonate. Where'd they get the bi from? Bi makes me think of 2, but it also means hydrogen. I don't like that one. Oops. So this happens a couple of other places. Here's hydrogen phosphate. Well, hydrogen phosphate is phosphate with a hydrogen ion on it. Hydrogen sulfite, HSO3, is sulfite with a hydrogen ion on it. Hydrogen sulfate is sulfate with a hydrogen ion on it. Okay? And then there's this guy, ammonium NH4+. That's the only positive ion we see in this table. That's a cation that's formed from nonmetals. So you can have an ionic compound that doesn't have any metals in it, but it's going to start with NH4. Okay? Let's see, where did we get to? So let's name some compounds here. So here we have MnNO2, 2. So when you read these formulas, you'd say MnNO2, 2. And saying 2 and 2 tells us it's different than 22. So we need to identify, first of all, make sure, is this an ionic compound? You look at the first element. Is it a metal? Yep, it's an ionic compound. Okay, this has 2 ions. So the first one is the Mn, and then everything else is the second one. Only 2 ions. So I've got Mn, and the other ion is NO3. Sorry, it's not NO3, it's NO2. And we memorize that the charge is -1. So when we're going to name this, we name the cation first. What's the name of that element? Manganese. Manganese and magnesium are sometimes confused, and then sometimes people get creative and say manganesium. That always makes me chuckle. Does manganese need a Roman numeral? Yeah, it's not in groups 1A, 2A, 3A, zinc, or silver. So I'm going to put a Roman numeral here. I don't know what it is yet. That's okay. So what's the name of this guy? Take a guess. Nitrite? Yeah, it is nitrite. Another great guess would be nitrate. Okay. So this is nitrite because nitrate is NO3. Yeah, memorize it. So this is manganese something nitrate. We have to figure out what the charge is on the manganese. Well, we've got 2 nitrite ions. That's a total of -2. How many manganese ions in the formula? Just the 1. So what would the charge on it be? 2+. Because the charge on this, combined with the charges on the 2 anions, we know there's 2 because it's in parentheses and there's a 2 on the outside. All those charges have to add up to 0. So manganese 2+, it's manganese 2 nitrite. The Roman numeral is the charge on the ion. It is not how many manganese ions are in the formula. It is related to and derived from that. It is a factor, but it's not the same number. Okay, what about this one? Looks like cocoa, doesn't it? This is C lowercase o and C capital O. It's not a typo, it's important. Okay, so we got two ions, CO and CO3. What's the name of that element? Cobalt. Does cobalt need a Roman numeral? Yep, not in groups 1A, 2A, 3A, zinc, or silver. This guy, what's a good guess for that name? Carbonate. Carbonate is correct. Because of the Roman numeral, we have to figure out what the charge is here. So what's the charge on carbonate ion? It's 2 minus. There's 1 carbonate, there's 1 cobalt. What's the charge on the cobalt? 2 plus. So what's the Roman numeral? 2. Questions?